The insertion in a B+Tree works by finding the leaf node where the insertion should happen at and inserting the entry. If there is room in the leaf node, this is just adding the data entry at the leaf node where the hierarchical search starting from the root will take us. But what if there is no room at the found leaf node? If there is no room at the found leaf node, there is a need for split operations. Split operation means adding a new node and dividing the keys in the leaf node between the two new nodes. This is in order to keep the minimum occupancy requirements. How do we point the intermediate nodes to the newly created node then? We add a pointer to the new leaf node to the parent tree node and repeat the same procedure recursively up. In a special case, where this ends up splitting our root node, we will add a new root node, increasing the height of the tree by 1. Let's see the insert operation using an example. Remember the same B+Tree we used for our lookup with equality search example. And assume we want to add a data entry with search key 8. This will belong to the leftmost leaf. However, this node is full and there is no space to add new data entry. So we have to do a split operation. Performing this, we will have 2 leaf nodes instead of the leftmost node. One including the entries for 2 and 3, and the other including the values for 5, 7, and the newly added 8. This split would need adding the new leaf nodes pointers to the parent node, which in this case is also the root node. Therefore, the entry 5 is added to the parent node. The pointers need to be updated to reflect pointers to the new nodes, and that means the root needs to split as well. In the non-leaf nodes, the nodes include index entries and not data entries. Therefore, when the split happens, instead of adding a new value, the middle entry should be pushed up. For example, the entry 17, which is the middle entry here, is pushed up. Since our splitted node was the root node, in this case the tree height is also increased. The rest of the pointers are updated accordingly. There's an alternative method to the insert algorithm. This variation of the algorithm will try to redistribute entries of a node with a sibling node before splitting the node. This algorithm maintains a higher average occupancy for the tree structure. For example, in the same tree, and inserting the data entry with search key 8, since the leftmost tree is full, but its sibling, which is the node immediately next to it that has pointers to it, only has 2 data entries, the data entry for 8 could be added to the sibling node. After this change, the key on the parent node that has a pointer to the leaf node has a new value. So we need to copy the value 8 and replace the previous entry to reflect the change. This needs ensuring that redistribution is possible, which needs checking the sibling node. Therefore, additional operation costs are involved in this method. If the sibling does not have a space for redistribution, the similar procedures of a split could be followed.